Good.
Yeah, thank you.
Okay, we are talking about a new type of optical surfaces. When I say optical surface, we are talking about the surface quality in terms of roughness as well as the waviness. Roughness is to be few nanometers, and the waviness, when I say waviness, is a departure from the designated prescription in terms of a fraction of a micron. Okay, let's get into the subject. Okay, the outline of my presentation would be, will be briefly talking about precision machining and then deterministic machining and what is single point diamond turning and the issues involved in single point diamond turning, and then we go for the case study, and then what are the new areas that we need to work in single point diamond turning. We'll talk about them. What is People talk about precision machining, precision engineering. But first, fundamental question is why we need to worry about precision in our machining. It is becoming not only very important, but also when you are going for nanometric surface qualities or submicron surface qualities and compacting the material, the workpieces, then precision is very important. Without precision, we cannot achieve our targeted goals. The parameters here are very important, which are dimensional accuracy, surface finish, edge quality, surface integrity, and the chips which are coming out during machining, they need to be controlled, and the cutting forces which are being uh, applicable on the surface is also very important. So this is a typical photograph of a single point diamond turning crystal is machining a workpiece, and there are many types of precision machining prevalent in the field, in the industry, as well as in the R&D areas: abrasion grinding, vacuum contouring, iron machining, iron deposition, and compressive molding, and process molding, and laser machining. And one of the very important precision machining areas include diamond turning. When I say diamond turning, using a diamond tipped tool as a for the machining. And this is a typical photograph of how the what you see here is primarily a brass surface which is being machined by a diamond tipped tool. This photograph is from our own laboratory. Why we need to do this? First and foremost, when the systems are becoming complex compact, and they wanted to be lightweight, so weight, volume, as well as footprint are becoming are being budgeted, and the materials selected for a particular application area, the materials are also as per the application, so the materials are also a constraint on selection. So these four parameters, weight, volume, footprint, and materials, are asking, demanding new types of surface generation for use in multiple applications. And so far, the normal spherical surfaces, concave or convex or flat surfaces, are not adequately giving the needed requirements in terms of optical system performance. So for that only, we need to go for new surfaces. And how we do that? New machines have come up with improved algorithms and are improved the controller accuracies, and also the memories have become very inexpensive. So this has given rise to excellent design growth, and then new fabrication methodologies and a new surface characterization and geometrical dimensional methodologies techniques have helped these new surfaces of submicron waviness as well as nano finish surfaces. What is the outcome? Outcome is wide material choices are there, process parameters can be controlled, can be monitored, thereby you get the desired surface quality and desired surface profile for a given application. And conventional fabrication methods is at the other side, and the another side is micro material removal techniques used, chemical methods or physical methods. We are somewhere in between. That is called a single point diamond turning. There is nothing like a single point theoretically, but the smallest possible contact point, we call it as a single point in the during the diamond turning process. So with the submicron waviness, as I already mentioned, the areas of application is strategic applications, space applications, astronomy application, biomedical, surveillance and public safety, virtual reality, augmented reality, many types of industrial and assistive devices for people with physically challenged. And then all these applications need different types of surfaces in their optical systems, which can be generated by using this precision fabrication and metrology expertise. Now, talking about determinism. What is determinism? Determinism is something when you determine this is what I want, this is what I don't want. Okay. The most basic rule of precision machining is determinism. System behavior. When a system, we are talking of the whole system here. We are not talking of a system performance. We are talking of the machining part here. When we are talking of a lathe machine or a see ultra high precision lathe machine and a tool, and then how it delivers the desired surface in terms of shape, form, figure, and finish. Form is a shape, figure is the departure from the RMS mean line of the profile, and then the finish. Finish is lack of roughness or desired amount of roughness. These three parameters, quality parameters, to meet them, what are the other parameters which can control them? We have to study. In the precision machining, precision engineering, all these parameters obey cause and effect relationships. We have to ensure that these causes are known, their corresponding effects need to be known, and then we need to either monitor them if we are unable to control them. If we can control them, we have to control in such a way that the quality is met. There is nothing like random here, and there is no probability here. Everything is deterministic. That's the meaning of deterministic. So what is deterministic? Dynamic variables and forces of a system acting at a given time, they determine the values of the variables at any later moment. So in other system, in other words, no randomness is involved. Randomness is eliminated. The deterministic model will always produce the same output from the same starting point and condition by following the same protocols of machining as well as metrology and characterization. So that is what determinism comes into play. What are the applications? If I have to go in detail, avionics, remote sensing, space instrumentation, missile technology, nuclear instrumentation, the list is endless. I have that's why written as etc. at the end. The ultra precision machining of deterministic nature would give the improved throughput, productivity, yield, and at a low cost. We are talking from industry, so obviously we have to look at uh, how inexpensively the procedure can be set up. What is the tool cost? What is the machining cost? What are the other parameters which cost us? How to reduce the cost? How to reduce the price? In other words, is very important for us. So, four parameters. One is the timely delivery, so high productivity we need. Second one is we need quality, no compromise on quality. Third one is whether it is applicable to the a particular given application or not. Last one is cost. As I was mentioning, form, figure, and finish. One is shape error, another is waviness error, the third one is finish error. But why do we need that? Just look at this figure. We are talking of an implant, an orthopedic implant. Here, if you look at the finish, the shining surface, here the roughness is very important. The reduction of roughness is very important. Similarly, the shape is also very important. So, form, figure, and finish are the three fundamental F's on which the single point diamond turning is completely based upon. If you have to see in terms of the departure, the black one line here is the desired surface, and these two lines correspond to the departure from the baseline and then waviness also, and this yellow color that you see here is the represents the roughness. So we have to control all the three. So how do we control? There are the parameters which are available to play around are tool overhang, what is the tool length, and the waviness, how do we compensate for the waviness on the surface, and what is the tool wear, and thermal issues, what happens to the heat that is being generated during machining, and then power spectral density of the roughness we are talking, the material properties, whether it is brittle or ductile, etc., they also come into play. And then finishing, how do we extra super finish the surface, and then subsurface damage, how do we ensure that the subsurface damage is at the minimum, because subsurface damage today you may not be able to see their effects, but over an extended periods of usage of the component in a given optical system, the surface damage would enhance exponentially and may damage the whole performance. So then vibration control, online metrology, these are the some of the issues that we have to worry. Now, who are the major players? What are the major players in precision machining? One is the material, because depending on the application, you select a material, and that's finished. And then next is machining conditions. Under what conditions we are machining? Third one is machining and tooling parameters. The final one is the protocols of fab and metrology. If we look at the material properties, it could be hardness, it could be toughness, ductility, brittleness, thermal properties, whether it is crystalline or amorphous. These five parameters would help you or resist your machining process. So these parameters we cannot do anything about it, because the material has been chosen as per the application. So you have to live with these parameters of material, and also Make sure that the material properties do not hamper your productivity nor increase your tool cost, etc. Then comes machining parameters. We are talking of tool feed rate or spindle speed, depth of cut, tool overhang. Tool overhang also plays a major role. There is a big study that we have conducted. For lack of time now, we are not going to get into that. Then machining conditions. Machining conditions, we talk about the coolant. What is your coolant? Whether it is leaving any marks on the surface or not, whether it is properly aligned with the tool job interface or not. That's also important. Maybe one of the slides I will show that. Ambient temperature. Temperature has to be controlled within plus or minus 1 degree, or best would be zero point 0.5 degrees centigrade, because we are talking of ultra high precision machining. There, the linear coefficient of thermal expansion of any metal would vary between 3.5 microns to 14 microns per degree centigrade per meter. So, the effect of the expansion should not have damage your surface quality. For that, ambient temperature needs to be maintained. Chip extractor is also very important. The position of chip extractor. If the chips are coming in between the tool and workpiece, then they will scratch the surface and they will damage the component. So you have to ensure that the chips are being extracted optimally. And then the humidity is also important. We have to maintain relative humidity between 45 to 55%. And the tool wear, we'll talk about tool wear a little later. Machining modes, whether we are doing a circular interpolation or a point to point interpolation, is also important. Talking about tool wear, what are the geometrical parameters of tool? We are using diamond as a tool here. Primarily a diamond tip mounted on a molybdenum shank is the tool here. If you can see on the right side, this black one is actually the diamond taken from the shadowgraph it is. And diamond being an octahedral crystal structure, we use that 110 or 111 uh, lattice axis to machine the component. It is the hardest material. At the same time, it is a fragile also when you are working away from this 111 and 101 110. These are the parameters: top rake angle, cylindrical conical edge, tool nose radius, cutting arc, offset angle, included angle, front clearance, second clearance, depths of the diamond, and then cutting height, tool nose waviness. If the tool nose is already having waviness in it, then it will be translated onto your workpiece. So ensure that the tool has minimum tool nose waviness, and the type of tool we are type of diamond that we are using, and then the shank specifications. What would happen if the tool has an error in its own form? It comes from two reasons. One is the tool, we have selected a tool with more waviness, or the tool is worn out over a period of time. Then what would happen? You can see here the red one is the tool tip and the blue one is the job. So if your tool is already worn out, then the form error, that shape error, would come into the workpiece. Second one is, how do you set the tool on the machine? Is it exactly at the center of the workpiece or not? In other words, we have to ensure that the tool tip center, workpiece center, the holder of the workpiece center, and then the spindle mesh, all these four need to be aligned within zero point 0.1 micron. Otherwise, if we don't do that, you what you can see, either it undercuts or it overcuts. If it undercuts, you are left with a cylinder at the center, as you see on the right side of the figure. If you overcut it, then you are left with a triangular trapezoidal thing at the center, which are not acceptable. See, this is it. When you take a micrograph of the machined surface, what you see is this, and then there is something called a ogive error will come into because of this undercutting or overcutting by the tool, by mis centering of the tool with respect to the workpiece. So we have to avoid these things. And what would happen if the tool is worn out? You can see on the left side, an unused tool and a worn out tool, and with a worn out tool, the surface quality naturally degrades. So then I mentioned about the spray mist. It has to be properly kept. This is it. It should be at the tool workpiece interface exactly positioned. And then how to hold the component also makes hell of a difference. If you are not, if you are an, you are not, putting with a 3-jaw chuck or a 4-jaw chuck, you are holding the job in a vacuum chuck. If the vacuum is high, then the workpiece bends, like you have seen this, behind the green workpiece, you can see those arrows, the workpiece bends. And one of my students has conducted a minor study, and he has seen that aluminum, copper, polycarbonate, and germanium, and this vacuum versus the deflection, he has measured that once you take out the job from the vacuum chuck, this will spring back, and the surface, instead of having a better form, you have a form error, that is a shape error. So you have to ensure optimum vacuum holding during the machining. So there is another thing: shape may be correct, but the form may be wrong, or figure may be not optimal. So for that, we do something called tool path compensation. You change the tool path minutely, micro in terms of micron, so that the job will come into the desired surface quality criteria. How do we do that? We start with a precision. Okay, we start with the machine, we machine it, and then we measure it, and then we do the metrology, and whatever error is there, we put this error in a negative feedback manner into the tool path, that the path the tool has to take over the surface, work surface, and then it fed back to the machine, and this the tool path is in that way it is changed slightly, and then within 2 3 cycles the component will come with a desired surface quality or reduced waviness. In terms of this, you can see here it starts with a nearly 7 microns of error and goes down to less than zero point 0.1 micron of error here. Now we go for a case study in which what we are doing is, let me go a little faster and then we'll come back. We are developing oxygen free high conducting copper mirror resonators for high power lasers. So here we are developing these oxygen-free high-conducting copper mirrors with a radius of curvature of 20,000 and 3% millimeter form error. And there, the challenge here is to develop a central lambda by 2 phase tip. When I say lambda, lambda is the wavelength, which is the wavelength of the laser beam, which is 10.3. It's a carbon dioxide laser we are talking. So with a hafnium oxide protective coating within the specified tolerances, this will be used as a rear mirror in the high power carbon dioxide laser resonator. Okay. Now, what is the challenge? The challenges are multiple here. First and foremost, you have to create a step with 250 plus or minus 50 micron diameter step, and the center at the center of the mirror, and the step height needs to be 5.3 micron exactly, because 5.3 is lambda by 2 for a 10.6 micron wavelength. So these are the objective, and how do we do that? Now we can see this is the plan. We start with a machining and then go for metrology, and then again we see one is a non-contact metrology, the CCA you have, and the contact metrology to measure the surface imperfections. So this is broadly the figure: a 50 mirror with approximately 10 thickness at the edges, and at the center the figure is drawn and not as per scale. At the center you can see approximately 250 plus or minus 50 50 micron diameter cylinder, which is actually the phase plate thing, and the radius of curvature of this surface is around 20,000 millimeters, and the height of this central cylinder is exactly 5.3 microns. How do we achieve this? That's what we are talking about. To generate this central cylinder, what we do is that, if you remember earlier, we mentioned about undercutting. If you do an undercutting, if you position your tool a little below the center of the workpiece, then you are left with a cylindrical errored surface at the center. Actually, that error we make use of in this case. The tool height with respect to the workpiece, we reduce it as per the diameter. We reduce, for example, you want a 258 micron diameter, so around 125 microns we keep the tool below the center of the workpiece, which is to be generated, and the phase step mirror. And then a cylindrical shape at the center would emerge after machining, because that is an art cut. So then, but there is a small problem here. The problem is, whenever you are doing any machining at the center, even though you ensure that there is the tool center, job center, workpiece center, and the spindle center are kept within zero point 0.1 micron, even less than that. That's a skill based thing and a image based exercise. Even then, there is a very small tip or pit will be there, that needs to be avoided. How do we do that? Very simple. The logic is, the component at the beginning itself, we put it off centered by, let's say, zero point 0.5 millimeters, way beyond the diameter of the step that we need to generate. So there the mirror surface is generated at diamond turned with a radius of curvature of approximately 20,000 or 20,000 millimeters, and then by machining this zero point 0.5 off center position, that error tip is also again taken away from the center. In the next step, this is how we do that. And next step, what we do is, mirror is once again realigned within 0.1, because the center tip has already gone a little away from the center, actual center of the component. Then we align this mirror with the spindle. This time it is reduced by 0.135 sorry, there is a typo error here. It is actually millimeter, 0.135 millimeters or 135 microns, so that the Diameter is around 275 from this spindle axis, and then we make one, instead of using the rough cut and a fine cut, we do two fine cuts. Each fine cut would be around 2.65 micron. So approximately we got 5.3 micron depth is cut, and this, that's how the mirror is done. And then this machining step results in a creation of a lambda by 2, that is 5.3 height, step height 5.313 with a diameter of arrow approximately 282. We have measured it, and the tip, that earlier small tip which you are talking, that is away from that. So during the final machining we remove that tip. So if you look at the flow chart, this is what we have done, this is how we have done. Starting from a copper disc, off centered by zero point 0.5, machined at that only with that offset, and then aligned with the spindle axis, and it is lowered by 135 microns, and then machining two machining cuts 2.65 microns each. So finally we left with a cylinder on the surface. That cylinder, we have taken the non-contact image. You can see this, there is no tip at the center, it is around 282 microns. The height is, we have measured the height also, you can see that is 0.5313 nanometers is the height. So that's how we have generated this desired surface quality, as well as the geometry of the resonator mirror for a high power laser beam with a waviness surface quality in terms of 0.1625. It is about lambda by 4 of a surface, and the radius of course approximately 20,000, and then the roughness is around 16.3 nanometers, 0.0163 nanometers, which is fairly very good surface, because the desired surface roughness was around 30 nanometers, and we have achieved less than half, around half of that. So here what I want to say is, for any given application, precision machining or precision engineering is a must. So in a given, we have presented a case study here of high power laser systems, where the resonators need to be of desired surface quality, which is better than lambda by 4 waviness and better than 30 nanometer roughness. So for this, precision machining is one of the methods that we have deployed here. And what are the future that we can do in this precision machining is, so far ductile materials are very easy to machine, but brittle materials have a big challenge in terms of tool wear as well as surface quality. That's one challenge that we want to do. Then thermal issues, what happens to the heat that is being generated while machining at the tool and jobs and interface, that we have to model, and we have to confirm, and we have to do compensatory machining for that. And then one biggest challenge nowadays we are facing is online metrology. While the job is, workpiece is being machined, metrology is not possible, which is done off the machining. So we have to do this online only, without removing the job from the vacuum check of the diamond turning machine. That is a challenge that some of my students are already working on that. Then what about the vibrations? Because vibrations cause uncontrolled roughness. For that we have to do something called a wavelet analysis. Start from first line fundamentals, and then we have to go all the way. And then tool wear modeling. What would happen if the tool is worn out? If the tool is worn out, there are two answers. One is that you change the tool or you relap the tool. In either way, first of all, when you change the tool, you lose precious tool setting hours, which reduces your productivity, and then tool cost would increase. So for that, how do we optimally use a given tool after it is set on the machine? For this, modeling is necessary, and then experimental verification is also necessary. Mentioned about wavelet analysis. Yeah, deterministic precision machining is also very important. Then you have to ensure that the pre-DTM stages of CNC machining and grinding polishing are need to be optimized, so that minimal effort and minimal time is taken at the stage of uh, diamond turning, because diamond turning is a very expensive process. And then simulation of the precision material removal is needed. So all said and done, then last thing is of course magnetorheological finishing is a very exciting and interesting area where we can deliver surface roughnesses of single digit nanometric roughnesses, 3 nanometer or 4 nanometer, depending on the application again. And single, how to, then one more thing is, one more issue that we need to worry about is, work on that is subsurface damage in terms of diagnostics, metrology, simulation, analysis, and optimization. And then we are talking of a rotationally symmetric surface, and how do we do about rotationally non-symmetric surfaces as well as the free-form surfaces. And this is a challenge for all optical system developers. And all said and done, I can say that the future of the diamond turning machining is very, very exciting. It's very, very challenging as well as very pleasantly promising. So I think I need to conclude. Before I conclude, I would like to acknowledge the work that is being done by my students, my colleagues, my teachers, and the vendors who have supplied us the wonderful equipment, and the organizations who have funded us, who have given an opportunity to work, and then the government of the country where I have been working, and then the whole diamond turning machining community. Thank you so very much. And then this is this is the cover page of one of the textbook that I have written along with my co-authors. Thank you so very much for your time and attention. God bless you all. Any questions?